Welcome. Let's read some mass spectrum. So simply speaking, mass spectrum is when you have a sample, you prepare in a various way, but you introduce to the machine where the vacuum is, and then you ionize them by electron, atoms, or laser, electricity, then have them fly. While they're flying, in order to reach the detector, we have them move around. Okay, we have them move just straight, time of flight, or we can have them oscillate, quadruple. We can have them curve. We can have them move in a cup. And then detection also, we can detect the ions directly, or we can read the frequency of the ions, the electric field, the changing. So in order to have them separate by their mass, like after fragmentation, you have a variety of the masses. We are using magnetic field or electric field, so they can show different behavior. Using them, we can change. Then the machines printing out this type of looking spectrum. So what happens in the mass instrument is, like we saw before, the analyzer, the magnetic sector analyzer with a certain curvature, the curvature is fixed. That we are changing the magnetic field in order to detect the mass. And then all the ions will have the same velocity. So those are fixed, and this is what we intentionally changing as an independent variable. And that's what we are measuring, right? Dependent variable. But I said the charge could be sometimes 2 or 3. So we know the curvature has to do with the charge as well. Therefore, the x-axis is not just the mass, but mass to charge ratio. That's what we are detecting. And then amount of the ion that's detected will make more current. More current. So it will give a bigger signal. Depends on how many ions you are detecting. That gives you Y value. And some instrument is detecting the fluctuation of the frequency of the electric field happening inside. So that can be also Y axis. If you compare to the spectroscopy, the X was a unit for the energy. So we are using frequency or wavelength as an x-axis. The Y was absorbance. That has to do with a couple of factors like absorptivity and the sample size and the concentrations. And here though it's completely different. So those spectroscopy tools, we hardly hurt the molecule. Sometimes UV spec has enough of energy to promote some photochemical reaction, so you can have cases where sample get destroyed or altered. But mass spec intentionally break it apart. So while you are doing it, what happens is, like, by changing the magnetic field, you are measuring this. But you have some method where you see their motions and how frequently they are rotating or coming back and forth or oscillating in the harmonic motion. You can change the intensity of the harmonic motion, so you can select and so on. So there we have angular velocity. You can connect the idea. So machine will change this. And then we will get this on the X. And then how many ions is there will give you Y, so you know that has to do with the stability. If you start breaking apart, sometimes you have a carbocation on the tertiary rather than primary. Then some primary can rearrange to the secondary or to the tertiary. So you'll, accumulating more concentration of the tertiary. So when you look at the structure, whole structure, you can see where you want to have a positive charge. And that's where you may expect some fragmentation taking place. So when you see spectrum, you find the tall signal and the shorter one, and then you can kind of say which ion is located here. You can get the idea as well as by the mass to charge ratio. Most of the time the charge is 1, so the number you see here is the mass unit of the molecule or the fragments. Also, I need to point out that we had a cases we changed the electric field plus minus voltages, so you can make changes on the charged particle with different mass instead of changing magnetic field. But in this relationship, you can see that changing of the electric field can also allow you to measure the mass to charge ratio. So whatever method you are using, we are getting spectrum this manner. And usually on the spectrum, the number for the mass to charge increases from 0 to the molecular weight. And there shouldn't be nothing greater, right? If you are measuring the whole molecule. So the biggest number you get is usually molecular peak. Sometimes the ions of molecules not stable enough, so it will break apart. So you are missing this. So you have a chance not to see this. So you don't always assume that the greatest number is molecular peak. Then you find the biggest, tallest peak. That's base peak, meaning the most stable ion. And there are some other peaks, including base peak, except the molecular peak. We call them fragment peak. There, so all of these are fragment peak, and that's molecular peak. And we are using symbol M to represent the molecular peak. So M, or sometimes you see this. Say this time this was a molecular peak of 100 mass unit with a +1 charge. So you will see 100, but there are many peaks. So which one? And obviously the tallest one, and that should be giving 100 in this case, okay? I mean, that's an example. Let's say that is the case. Then when you look at this peak, bunch of peak, say you got this tallest one as a 75. And then second one as 60, for example, okay? Then we can label this peak and this fragment peaks this way. M minus the difference between this and this, right, is 25. So M minus 25. Then we label this as M minus 40. This way. What it means is when you have a whole molecule with a molecular weight of 100, you lost 25 of mass and you have 75 left. Then this fragment, you lost more, 15 more, total of 40 you lost out of 100 mass unit. So you chopped, big piece off. and you have only 60 left. Okay, so you can label these fragment peaks this way. Also, when you look at each group of peaks, you have these little peaks, so you can label these as well, like this one here, 1 unit less, so m-1. Okay, this one is 1 unit greater, so m+1. This one m+2, and so on. And it's not always the case, but most of the time these are isotopes. You know about the natural abundance of isotopes, right? That's why we get the atomic weight and the molecular weight. That's the average of all the naturally abundant isotopes of each element. For example, so if you calculate the molecular weight of this chemical, it will be 100.15888. But the spectrum don't show that. That's because the molecular weight is calculated by the atomic weight of each atom. But each atom, if you think about it in nature, carbons are not always carbon-12. Hydrogen is not always hydrogen-12. Okay, some you have when you have a mole of this molecule, some molecule has carbon-13 isotope instead of 12. Some less likely, but you have 2 of carbon-13 there. And you have chance to get the deuterium instead of hydrogen. And when you have a more number of hydrogen than carbon, then you have a more chance of getting 2 deuterium in some molecule. Oxygen, same. So naturally, when you deal with a mole number of group of molecules, you have to use average of them. Okay, but when you measure individual molecules, individual molecule may have just all carbon-12, all hydrogen-1, all oxygen-16. And when you measure that, it's not going to be this. And when you measure molecule with 1 deuterium instead of hydrogen, now the measurement will give you 101 something. Okay, when you measure carbon-12, 5 of them, and the 1 carbon-13 and 11 hydrogen and 1 deuterium and oxygen, then the measurement should be 102 instead of 100, 102 something. So when the most of the atoms, they're with the most abundant atom of each type, just like carbon-12, hydrogen-1, oxygen-16, then you get the most abundant, tallest peak. Okay, say that was 100. Then you have m+1, m+2, So those isotopes embedded in certain particular molecule. There's no difference in structure, but you have the replacement of hydrogen or carbon or oxygen with the different isotopes. Then that molecule, the very molecule with the isotope in it, should have more weight. And they're less likely. Having 1 is less likely. Having 2 is much weaker, less likely, even more. That's why the peaks are small. So how smaller it is, if you know by reading the Y value, then you are basically able to calculate natural abundance. And that natural abundance is giving you the hint of what type of atoms and how many of them you have using your mathematical skill. I mean, it's just the algebraic skill. You can calculate them out. And these are the some numbers I can tell you that, as you can see, okay, this is a switched. So natural carbon-12 is 99% nearly. Only around 1% is carbon-13. So size of the signal wise, carbon doesn't change much of the intensity for isotope peaks. Hydrogen also 99.99% even. So almost all hydrogens are hydrogen 1. Oxygen 16, 99%. Nitrogen 14, 99%. So most of the time when you have a carbon, hydrogen, oxygen, nitrogen, these regular organic compound made of these common atoms, the M+1 is about like what, 1%. So 1% of this is like not this tall, right? Very tiny. If you see the M+1 peak here is taller than 1% or little more, then you have to worry about having other isotopes. And among them, there is a unique atoms that gives you extremely tall M+2 peaks. Normally M+2 peak has to be smaller than M+1 because the probability of having two isotopes is lower than having one isotope in the molecule. But atoms like a chlorine, if you have a one chlorine isotope, you have a +2, okay, not +1. Bromine also, if you have a one bromine isotope, you increase the mass by 2 units. So you have a M, but then you have a M+2, okay. How tall are they? If you have a chlorine, one chlorine in the molecule, you get about 25% size of the signal, okay, quarter. Not really quarter, 75 versus 25, so it's about 1/3, okay. If you have a one bromine, signal for M, the molecular peak, versus molecular peak +2, M+2 peak with the isotope, right, is as tall as M. So basically, normally with the other atoms, your peaks are just like this. And you see tiny one with one more unit. But when you have a chlorine, one chlorine on it, whatever the molecular weight of the molecule with the chlorine in it might be, okay, it could be 100, it could be 120, whatever, then you expect M+2, say molecular weight was 100 with the chlorine in it, then you should see 102 becoming 1/3. This is almost half, I'm sorry. It should be almost 1/3 size of the molecular peak. Then you know presence of this size of the M+2 peak is telling you that you have one chlorine in the molecule. Okay, if you have a bromine, then you should have M and the M+2. Okay, M+1 might be small, but M+2 as tall as M, almost in a twin tower. Then you know this compound has a bromine in it. If you recall from the IR, the presence of chlorine and the bromine is difficult to detect. In old days, we used to flame test or silver nitrate tests, but they're not very specific. But with a mass spec, you can check the presence of chlorine leaving group or bromine leaving group, And if you have more than one, you can think of having n plus 4, right? Because you have one more, and you can calculate the chances. I mean the intensity of the peaks. There, it's just fun. It is fun if you try figuring out these numbers, but I did it quickly. And when you have two chlorines, M, all chlorine 35s, okay, two of them, that's the molecular peak. When you have a 135 chlorine, 137 isotope chlorine, it's about 64% of the intensity of the M peak. The chance to have both chlorine 37, you know, the abundance is only 24%. So about 24% of 24%. So it's about this intensity. So bang, bang, bang. You have some significant size though. Okay. Like I said, if you have only these guys, this should be really small. I mean, n plus 1 is really small, n plus 2 is very, very small, n plus 4 will be almost the 0, right? You don't see it, but you see some size, then you know this is the case. You have a chlorine, but not just one, but two chlorines. When you have a bromine, that's natural abundance of 50-50 nearly. When you have two of them, the molecular peak, when it's this intense, the chance to have one, okay, both having just 79 is even less likely. When you have two, you should have only at least one of them having 81, right? That's natural abundance. When you pick two, in the probability, you have to pick one of this, one of that. That's natural. So that's really natural. That's the most likely case. Oh, what's happening here? I'm sorry. I was rushing. 51 point. So this is natural case with the one n plus 2 isotope embedded n plus 2 peaks tallest, then having both of them bromine, both of the bromine being 81 isotope, that's about half chance. Okay, so this is how you know you have two bromines in the molecule. So when you see the mass spec, you check the molecular peak and making sure it is indeed a molecular peak. Okay, you may miss this peak sometimes. Then checking the charge would be +1, which is normally the case, especially for sophomore organic chemistry students. You don't need to really worry about this charge. Then you look at the isotope peaks. See, you have n plus 2 peak significantly big, like a chlorine or a bromine, or sometimes with the other heavy atoms, you may have a significantly big n plus 1 isotope peak as well. And that means you have more than just the carbon, hydrogen, oxygen, nitrogens. Okay. Then you look for the loss, the fragmentation, how much you lost. That will give you some idea. That's what I'm going to talk about now. Then while you are looking for fragmentation pattern, you need to be able to explain the most stable peak with a certain mass. I don't know what it is. Let's say this is 40. Then the mass unit of 40 should be in the structure that's most stable, because it's giving the base peak, the tallest peak. So it is all under the fragmentation. So let's get to the fragmentation. Okay, let's take a look at this molecule spectrum, mass spectrum of it. Propyl bromide, right? 1-bromopropane. The molecular weight of it, if you calculate using the atomic mass on the periodic table, which are the average of all the isotopes like I mentioned, it should be about 122.99. Okay, but if you read the molecular peak area, there's no 122.99 because they're not average of the molecules with different isotopes. Okay, so this 122 and the 124 you see, and since you have one bromine, you have only two towers. So 122 is the molecule with the regular carbon hydrogens plus 79 isotope of bromine. That's 122. 124 is same carbon hydrogen with a regular, 99% of them are anyway regular, but 50% of the bromine is 81. So this is M, that's M plus 2. No one's labeling it for you, so you need to label it as M and M plus 2. Then you have base peak here, the tallest peak, okay? And you read the number down there, and you calculate, number is 43, then subtract 143 from 122, then you get 79. Okay, but then why don't you have a twin tower here? That tells you that you lost what? Bromine. Okay, because whatever the molecule here is after fragmented, you don't have a bromine. That's why it's only one tower with a little isotope peaks right there. That's a regular size isotope peak. The fragment or molecule that has bromine will show you twin tower. Say you did not lose bromine, but you lost a carbon only, then you gotta have a twin tower with a less mass unit. How much? Carbon 12, hydrogen 3 of them, so total 15 less than 122. So you gotta have 2 peaks around here, because you still have a bromine, but it's not the case here, okay? So you lost the bromine because that bond is weakest and the molecule is smashed by something in the machine, so you break the weakest bond anyway. So you lost the bromine and you get this peak without bromine, and this is a base peak. So your loss is 79, matching with the bromine. So what's left here is a CH3, CH2, and the CH2. So that's the ion you detected, and that's a fragment. That's not the whole molecule. This is whole molecule. Okay. This molecule is dead cane. Okay. And luckily, we have a peak here, very small, meaning the molecular peak after losing one electron is not stable, so it fragmented quickly. But you have the peak, and that's the M, molecular peak. Then the next one you see is 113. Okay. Sometimes small peaks like IR are not trustable, so I usually go for the taller ones and try to figure out what they are. Okay, I need to show you how to do those things. And we need to skill that we used for the formula analysis. Also, when you talk about fragmentation, you need knowledge from the radical reactions. As you saw before, knocking out one electron made the cationic radical. So radical and the formula analysis become very crucial skill in the mass spec analysis. But anyway, next one is 113. I'm trying to show you the fragmentation. Okay, I'm not trying to tell you this is the way you read in the order. Like I said, I'm going the big one first. So in the sake of telling you the fragmentation, how much you lost here? 29. So what is 29? I can tell you answer already. If you look at it, 29 you can make it. The CH3 is 15, CH2 is 14, so together 29. So basically this fragment peak is a measure of weight of the remaining 8 carbon positive ion after losing this C2H5. Then from there, how much you lost? This is M minus 29, right? So how much more you lost? 14. So meaning you lost this. The next one, you should lose this. If the isomer you are thinking is correct in this way, you should lose 14 more, 14 more, 14 more, 14 more. Then you get the 43. Okay, that's the one that you lost. I mean, you have left after losing so many weight. Therefore, in order to understand the fragmentation better in figuring out the structures, you need to analyze the formula. But this time you don't have a formula, you have number. You have to come up with a formula to guess what you have lost. So first, from our previous spectrum, we lost 29. We got M29 peak. So we need to understand what is 29. Okay. I mean, this is a so typical one, so it's easy, but let's just try. First, we have to assume, okay, that we may have lost 1 carbon. But to make up 29 with a 1 carbon, which is 12, you need to lose 17 hydrogens. But how can you lose a CH17? It's not possible. Maximum hydrogen you can put on the 1 carbon is 4, right? So that's not good guess. And if you think of losing 2 carbons in loss of 29, 2 carbon is 12 times 2, so 24, so 5 hydrogens. Is it possible? If this molecule, I mean this fragment, which is molecule, ion, by the way, is alkane, for example, that's the maximum hydrogen you could have when it's alkane, right? So with a plus charge, you know you lost 1 bond. Therefore, Cn plus 2. So 2, so Cn2 times 2 plus 2, but it's positive, so minus 1. 4, 6, 5, because it's a positive. So perfect. This is regular CC with the maximum hydrogen, the alkane one. Can it be with a 3 carbon loss? When it's a 3 carbon loss, it's already 36. 12 times 3, 36, more than 29. So it's not good. So we know what we lost is a CH3 and the CH2. So as you can see, the skill we practiced with the formula analysis in previous video is very crucial. Let's try to read this mass spec. There is your base peak, most stable ion, and that's a molecular peak. Again, somehow this molecule is not stable with a plus charge. So let me label them and come back. Something like that, okay? So this 137 peak is the fragment after losing 43, and this 120, the stable one, is after losing 43, lost 17. Or it may not be the sequential one, okay? So it could be just one chunk of a 60 from other part of the molecule. You never know. So figure out what makes 43. And notice there is a signal for 43 as well. So here is what I did for you. If you think of the 2 carbon, then you should have a 19 hydrogen, considering it is a fragment with a plus sign, meaning lost 1 bond, and that's impossible having 19 on the 2 carbons. But having 3 carbon with a 7 hydrogen is giving 43. But I could think of having 2 carbons, 3 hydrogens, and 1 oxygen can be also 43. So if you draw them out, is this, because if it's alkane, right, the formula will be 2 times n plus 2, but lost 1 bond in the fragmentation is this. So this is alkane formula. So you know this is alkane with 3 carbon. But what is this? What can you do? Again, with oxygen in it, the H number is 2 times 2, the number of carbon, plus 2 minus 1. Having 1 oxygen do not change number of hydrogen, right? If it's alkane, it should be this formula. So C2H4, 5, 6, minus 1, 5, or plus. So when you compare, you are losing 2 hydrogen. Index of degree of unsaturation is 1. So you have 1 double bond or 1 ring. Okay, with the 2 carbon and oxygen, having ring is not common. I mean, it's possible, but it's not common. So if you consider double bond, you can think of this fragment as a CH3CO, right? This way, and the positive here, meaning the acetyl group was somewhere. Okay. So then how would you check presence of carbonyl? What if this was a CH2NCHO having oxygen bound to some molecule, the other part of the molecule, not the double bonded one on the CO. You go to the IR and you can check whether your molecule has a carbonyl group around 1700, or you have a sp2 carbon CH stretching over 3000, or you have a peak of the carbon-carbon double bond, which is very tricky because it's near the bending vibration, but you check that, or you check the presence of a strong CO single bond at 1 or 2. You can choose that way using IR, but mass spec gave you this idea. Then this peak, the most stable one, lost 17 more. So what is it? What makes 17? It's very difficult with just the carbon in it. If you think about it, just carbon 12, okay, 4 more carbon would be 16. So to be 17, you need to have 1 more hydrogen, and that's not possible. So most likely 17 would be oxygen 16 with a 1 hydrogen. So OH, you have OH. So you lost OH. So you first lost this, then you lost that. And the remaining molecule has the weight of 120. It's still very big molecule. It's around 10, right? I mean, 10 carbon makes 120, but then you don't have any hydrogen. It's weird. So maybe it's not 10 carbon, but it's a fairly big molecule. Okay, what if they gave you this formula? Then to analyze this formula for unsaturation, you do this for alkane formula, and oxygen don't change the hydrogen number, so you come up with a 20. Then the missing hydrogen number would be, then the losing 12 hydrogen, degree of unsaturation becomes 6. But when the degree of unsaturation is over 4, you should consider having benzene. So benzene is 4 of degree of unsaturation. So what's remaining is 2. So you should consider benzene. Then you still have 2 more. meaning you may have triple bond or two double bonds or two rings or one double bond and one ring, like this. Since we know there's a benzene, we're expecting the benzene comes around here, right? So I sort of try to calculate the rough number. If you have a benzene with a 6 carbon and we don't know how many hydrogens got replaced with a substituent, so we just say roughly speaking 4 to 5 hydrogen. So 70 plus 4 to 5, that would be 76, 77, who knows, plus minus 1 or 2, right? And the closest number is 92. So definitely it's not the case of losing 60 and the benzene is part of the 60. It's not the case. This is including benzene in it, okay? And also this must be including benzene in it. And the loss of the 43 could be this, or could be the propyl group. But since we have many oxygens, right, we need to consider that. We may have more chance to lose this one in loss of 43. And loss of 60, here we lost probably this and OH, not benzene. So benzene still here. And also we need to lose 2 index of hydrogen deficiency. So we lost here carbonyl group, then you have 1 left because you used the 1 deficiency right there. At the same time, if you think about it, we have a total number of 9 carbons, and you have a benzene, then you use the 6 of the 9. If you lost this, then you used 2 more, so 8, meaning you have 1 more carbon somewhere on the ring. Okay, so let's include carbon in the formula to make up 92. That adds up to the 88 to 89. Then the carbon wouldn't be just carbon, it could have a couple hydrogens, so I think we can make up 92 soon. Meaning the benzene on this peak, you have a carbon. Don't know how many hydrogens are there, but this is making up 92. We need to calculate. And by the way, since we have so many oxygens in the formula, I used the oxygen and they came up with this formula that is 92. Then if you calculate the index of hydrogen deficiency, degree of unsaturation, then the degree of unsaturation can be 5. However, don't forget, it's greater than 4, so you can think of having benzene and then you can have oxygen there, and that is not 92, right? And also this is not complete molecule, you need 1 more bonding there. So if you lose 1 more hydrogen on this somewhere, say you lost 1 there, then you lost 2 hydrogens. So here you have a 5 degree of unsaturation, and you lost 10 hydrogen. See, 14 minus 4, right? 10. So 2 hydrogen, 4, 6, 8, 9, 10 hydrogens lost. So that makes sense. This means that you have something attached on the oxygen and some other group attached on the ring, and it could be anywhere. We have no idea where, but you have 1 more attachment, leaving only 4 hydrogens. And out of 6, you have 2 attachment total, so 4. and that also makes up 92. Since we found this, let's examine this our proposition more carefully. So we are saying there are 7 carbons, and in order to make up 92, how many hydrogens are required? 7 times 12 is 84. So in order to be 92, you need 8 hydrogens, meaning 1, 2, 3, 4, 5. So you need 3 more hydrogens. So if you want to have a carbon instead of oxygen, you cannot attach anything else. You make up 92, yes, but that's it. You cannot attach anymore. So this idea is not valid. Indeed, the one with the oxygen works better. So you have something attached here, something attached anywhere on the ring. Let's just say this is the case. So that's the 92. Then I found 28. And also here is the tricky to find the fragment that's lost. If you have 2 carbons, that's already 24, and 4 hydrogen could be 28. Okay, so let's think about 28. So this is 28, but problem with this idea is we have only 9 carbons, and we found 6 here, and then 7, 8. Okay, so we can use only 1 more carbon. We cannot use 2, so not a valid idea. So 1 carbon. Then how many oxygens we have used? We used 1, 2, and 3. So we need to use 1 more oxygen to make up this. After losing this and this, we need to lose 28 more, and that should be just using 1 carbon and 1 oxygen. And how many hydrogen? We need to worry about that later, but together I think it just makes up 28, right? Meaning they're together, CO, bonded. Is it single bonded or double bonded? Let's think about it. So we included the benzene ring that takes up the 4 index of hydrogen deficiency. We had 2 left, and the one used here, okay, when you lose 43, right, we used it. So out of 2, we used the 1, so we need 1 more. That means this can be CO double bond. Then no more ring, no more pi bonds. So this loss of 28 is CO double bond. Then how many oxygens we used? 1, 2, 3, 4. How many carbons we used? 6, 7, 8, 9. So how many hydrogen finally? 4, okay, 3, so 3, so 7, 1, 8. So we found everything. We just need to put them all together. There are a couple ways, but let me show you this one of the possible isomers that we can put together. On the oxygen, you can put this acetyl group that we lost first, right? And then let's put this carbonyl group, and then OH group. That's one possible isomers that fit into this mass spec. If we have IR, then we would be able to check whether this is a good or not. That's why eventually we have to study how to solve the problem with the IR and the mass. then later NMR, IR, mass, then UV, NMR, IR, and the mass. So we have to expand it that way. So we still are in the beginning of the reading mass spec, but I'm just trying to make a point. You know, the formula analysis is very important in the learning the idea of the structures of fragments. That allows us to come up with the overall structures. It's fairly difficult for the big molecule, but with the small molecules it's doable. And many times you have other spectrums given with the mass spec, so it would be more helpful and easier. Okay, these are the common fragments you run into during the fragment analysis. Like we've seen couple, but 15 is like a methyl group loss, and 17 OH, 18 water, 26 can be CH triple bond CH or CN triple bond, 28 very common CH2 double bonded nitrogen or CO double bond like we saw before, and then CH2 double bonded to Cl, CH2, and so on. And also when you lose one, it's normally aldehyde, so the whole molecular weight -1, that peak, if you see intense peak of M-1, that's normally is the sign of aldehyde. And you can see very extensive table online, or you have a book like hundreds of pages of possible fragment with the very high resolution, like 15.0001 something, 0.002 something else. There are all kinds of combinations of common fragments, books even they have. But for you guys, I know memorizing them even also is very difficult. So like I showed you before, it looks very tedious, but if you practice few times it becomes better. Then you don't need to memorize them. However, some of them you pick and memorize, some common things, right? It can be helpful, like 91 for the carbon, but the case you saw before wasn't the CH2, it was oxygen when it's not 91, but similar number. So again, memorizing is not always the best idea, but who knows, memorizing 43 for acetyl group, because acetyl is so common, and the 28 for CO double bond, I mean, it could help, but my advice is analyze it instead of memorizing. So basically we cover noticing the molecular peaks, fragment peaks, the base peaks. You have to eventually make sure your assumption, your presumed structure is able to make up the base peak after breaking apart other pieces. And then you have to also rely on the isotope peaks for certain cases. And then the fragmentation pattern will give you an idea of the overall structure. So let's now talk about how the molecules are fragmenting. What are the typical mechanisms? First, when you try to ionize them, obviously losing electrons from the lone pairs of all type of heteroatoms, those are easier. If you don't have them, then you can assume one of the pi bonds is partially broken, so it's difficult to show, but one of the bond is broken, and you have a radical cation. This as well, you broke the pi bond and radical cation exist, whichever carbon's better to be cation, you know, more degree carbon is better to have a plus charge. But even sigma bond can lose one electron. It's difficult to show without quantum mechanical picture, so you can draw it this way. So once you ionize them this way, you have to look into their fragmentation mechanism. So there are a couple types. Just like these cases, right? You can think of breaking off these leaving group kind of positive ions. You can think of like water, you know, when you lose water in SN1. These two electrons go. Then the chlorine gains 2 electrons, so it becomes radical, losing plus charge. But this part becomes positive charge. This as well, whichever is more stable with a positive charge will break off, right, and become positive. And this as well will give electron to the positive nitrogen. And here there is a slight difference, but you can break one of these two as well. That's simple. So we can say this alpha cleavage right there, right? Alpha carbon right there. Number 2. Okay, alpha cleavage in ionic mechanism, like a hetero cleavage. But you can have another alpha cleavage radically by homolytic cleavage. So what could happen is, instead of doing that, let me show you. If you have a certain heteroatom that was a radical cation, you could do that and see loss of this much in the fragmentation. But sometimes you see losing more at once. It could be sequential, lose this much, then lose that much sequentially, but sometimes you lose a big chunk, right? That's probably because this cation is more stable or have a resonance or something. But when that happens, you can actually have forming double bond here, and this breaks up there. And then what will happen is actually R becomes radical, and this part becomes positive, and you will be able to detect this. This is what we saw before. Like, we lost this, but we detected this because this became positive, that kind of thing. Some other case, you can have an elimination, kind of, you know, resembles elimination mechanism. So when you have hydrogen next to each other, you know, when you have a OH, this happens a lot, but it could happen with other groups. So let me just put it in general. So radical positive after, say, oxygen or these things lost electron. Not only they're able to break here, also here in the cleavage, you can break the bond radically here to detect this part, right? But you can also do that. this hydrogen is somehow reacting with this heteroatom. Radical goes here, and then the electron, because of the plus charge, both electron goes. So what's happening is eventually you make the partial double bond, because you gain one and lost two, become positive cation, just like I mentioned earlier, and then you lose this. If this was OH, instead of losing 17, you can lose 18. That's the mechanism. So let's practice a couple of these with a real functional group before we wrap up. So here, if you have this molecule, you can ionize them and then break it there, right? And then make up this cation, and you detect. And this will be neutral radical, it wouldn't be detected. That was the first mechanism. The second mechanism, the homolytic cleavage on the alpha carbon was, let me redraw this molecule. So instead of breaking here, right, you give one electron here and get there, and then you give this. So methyl group radical is lost, and that's neutral, not detectable because it's not charged. Here you can detect this piece. That's the second mechanism. And then the third mechanism is you do this cleavage, sort of beta cleavage, and you're losing here also. So alpha heterolytic cleavage, and you lose water, neutral molecule, loss of 18, then you are detecting this. So out of one molecule, you can fragment it into 3 different ways. And then if this molecule you created, ions are bigger, even this one could do, but this can go further fragmentation. And if you had alkene, rather than breaking here, you would break there when this is positively charged. By breaking here, giving electron this way, right? Breaking there, you are making this piece, charged piece. Well, you cannot do that, so you don't form bond here, then the electron goes there and become positive. So yeah, you can detect this molecule. Wait, thinking of it, it's gonna be positive over here, because electron radical moved there and formed double bond. This was originally a partial bond, so one electron moved away, so this carbon has to be positive. So anyway, this positive cation will be detected with a double bond. Same for the benzene. If you have a benzene ring and you have a more chain, most likely you're gonna break there instead of here. And if you have a sigma bond alkane molecule only, something like this, right? Most likely you're gonna break not here, but one of these bonds, so you can create tertiary carbocation, and that probably becomes the base peak. And here as well, if you have more carbons, you can break other plates and make a smaller peaks, but by breaking here, you are creating most stable base peak this way. And you know, out of all these possible fragmentation mechanisms, you can also estimate which one's the most stable and think of the possible base peak. Okay, so let's wrap up. Look for the molecular peak and calculating the isotope peaks. You can get idea of the formula or the presence of certain elements, and then analyzing the fragmentation pattern. You understand, you know, while they're flying, what's happening, and that gives you idea of what pieces you detected are making up the whole molecule. In doing so, formula analysis became important to guess the pieces with a certain unit of weight. And then the fragmentation mechanism around the heteroatoms and the double bond, triple bond, will help you to guess the structure of the pieces. Thus, you are able to construct the molecular structure that has a certain molecular weight. And in conjunction with the other spectroscopy, it becomes a lot more easy task. So on next video, we should be practicing on working with the other spectrum, starting with the IR. So I'll have next video working on the spectrum of mass spec and the IR spec. So until then, keep up the practicing. Bye.